Stanford University Student Robotics is proud to present our 2019 Mars rover. We've been working hard to improve on lessons learned from our first competition, and we're excited to show you our progress. Our team, composed of half freshmen and half upperclassmen, is subdivided by subsystem: drive, arm, and science, which allows for tighter integration between the mechanical, electrical, and software designs.
This year's drive base uses a 6-wheel rocker suspension design for handling the extreme competition terrain. During last year's competition, our rover flipped during the first task. To fix this, we experimented with several designs and settled on this wheelbase and rocket geometry, which are optimized to have a virtual point of rotation below the ground and a low center of mass. Powerful, readily available hub motors allow us to climb steep slopes and over obstacles. Nylon chains provide traction on slippery terrain, and inflated wheels absorb the shock of drops. The chassis is made of aluminum extrusion bolted together with custom water jet brackets. The easily sourced materials make parts quick to manufacture and replace.
For the equipment servicing task, our rover uses a 6 degree of freedom SCARA arm. The SCARA design allows us to move in plane with finer control and less strain on our motors. Our robot is fully operable using a single gamepad, meaning even a solo operator can practice driving the robot. Given predominantly vertical loads, we increase strength along the Z-axis while keeping the overall weight of the arm down. Our end effector uses a lead screw for a strong, non-backdrivable grip. The fingers will be swappable for soil sampling, carrying heavy objects, and fine manipulation. Last year, we struggled with slop and inaccuracy in our arm joints. To fix this, we constructed our joints by clamping thrust bearings with shoulder bolts, allowing for extremely low play. For intuitive control, the arm uses a custom inverse kinematics model that precisely controls the end effector position and gracefully handles singularities. We also have many adjustable camera views. Low latency cameras provide fluid, responsive feedback, and a high-res pan-tilt zoom camera allows precision teleoperation. We also have an e-stop in case the rover causes trouble.
We are using fluorescence microscopy with modular filters, light sources, and fluorophores to detect life in soil.
Using fluorescence microscopy allows for unparalleled sensitivity while allowing for detection of many different biomarkers. To maneuver the soil into a position where it can be assayed, we are using a spinning apparatus.
After soil is added using a mechanical arm, the entire system spins rapidly to move solid dirt to the bottom of the cuvette. Light passes through the sample from an LED on the inside of the device to a camera opposite. Presence of a fluorophore will cause the sample to fluoresce if a biomarker is present. Sensitivity is increased through the use of 2 replaceable filters. Our proof of concept uses Cytox Orange, a fluorophore which binds specifically to nucleic acids. Due to the adaptability of our system, this could be easily changed in order to detect different organic molecules, such as proteins or sugars.
For the autonomy task, the operator will be able to specify multiple waypoints and obstacles to avoid on a map interface. A path is then generated for the rover to follow. This path will be dynamically modified to reroute around obstacles detected by the onboard LiDAR. Our RTK GPS is able to achieve centimeter-level accuracy, and IMU sensor fusion allows us to robustly determine orientation. Finally, we use computer vision to identify the tennis ball.
Overall, our system design priorities this year have been robustness and ease of use. Our design philosophy was to rush to a minimum viable rover with rapid prototyping and improve issues as they come up. We believe this leads to a more robust final design that addresses features essential for competition success. Each subsystem has a hardened Linux node powered and networked over Ethernet, which communicates over our custom lightweight protocol. For long-range communications, we use an off-the-shelf 2.4 GHz antenna system, which we found to deliver high reliability and throughput in last year's competition.
We are proud of how far we've come this year, and we are excited to compete in the University Rover Challenge.